Hey guys, welcome back to the channel. Today we'll be doing the episode number 4 for creating our custom ray tracer in C++ and Unreal Engine. So the last time we left off, we created our first image in Unreal Engine or our ray tracer, which was a UV coordinate or texture coordinate. So we have this beautiful gradient from black to red and green to red and whatever, right? In today's episode, however, we'll be doing our first ray traced image. So we'll first create a circle to the screen, and then we'll create a material to make that circle seem have the perception of depth to it, right? So with that said, let's actually get right into it. So this is what we have from the previous episode, as I showed earlier. And let's open our okay, so I don't have my ray tracer class open, so let's wait for that to load. And here we go. So let's open our raytracer.cpp and come to the section where we defined our colors here. So you remember the last episode, we actually defined a couple of pixel location values. So the pixel location 00 and the pixel delta u and v. Make sure you take the declaration and declare it before the class initialization. So make sure you take all those vectors and put it on top, because we'll be using this in a global context. So make sure you have pixel location 00, pixel delta u, and a look from position, right? Now let's come down to our actual loop here, and we don't actually want to deal with our GB values we are calculating. So let's get rid of that, and let's define a f vector, which is going to be the pixel center. And as I mentioned in the theory part, or not the theory part, I think the last episode actually, we should raise to the center of each pixel. So that's what we call calculating here. So we just have to ask the pixel location 00 plus I into pixel delta u plus j into pixel delta v. So pixel delta v and u, as I mentioned earlier, it's more like an increment, so it's a scrolling vector along the viewport. And once we have that, we actually need to define a direction. So the direction, we need to shoot the ray through the pixel center, right? And we can actually do that pretty simply. We can just declare variable direction, and we can just say pixel center minus look from, right? So this becomes our direction for the ray to begin. So just with these two values, we're not going to do much. So let me actually delete these values as well. And let's actually keep the pixel color for now. Make everything 00. And let's define our ray color function. So this function is actually going to calculate the ray trace hit points and then return the color based on the diffuse shaders that will be, or the shaders materials actually. So based on the materials, the ray color function is going to return the color values, right? We are actually going to define it in raytracer H. Come all the way down to our private. We have private section for functions, and return a f vector, and we can call that ray color, right? You can actually use f color here or any color vector, but just to follow along with my previous project, so it's easy for me to debug, I'm using f vector here because we'll be doing gamma correction later on, and it's easier to do it with f vector rather than linear color with the ranges and stuff. So you can actually use f color and see how that goes. And the argument is going to take depth value again. The argument is going to take a depth value, so that should indicate this is a recursive function, and we'll also take an f vector of start location, an f vector of direction. I'm actually going to call this rate direction, and here we go, right? And we'll create a definition. I think in the last videos I actually called that declaration, so that's my bad. It's creating definition, obviously. So the first thing we want to do is, since this is going to be a recursive function, we obviously need a base statement, so base case. Otherwise we'll have a Stack Overflow and then crash the entire application. So our base case, when you think about it, is in the theory part I mentioned, we'll use the max depth to create shadows. So when we reach a max depth, we'll actually return a color value. So this is the part where you can be, you have creative freedom to define your shadow colors. Basically, if you return red color here, your entire shadows is going to be red color. If it's green, your shadows are going to be green. But to keep up with the realism, we are actually going to return a black color, right? So if depth is less than or equal to 0, we'll return a f vector of 0, 0, 0, right? So that's going to be our shadow color, right? Once that's done, the next thing we want to do is actually calculate the end direction. Now, here's the thing. We're doing Unreal Engine and Unity, or whatever you're following along, a game engine, hopefully, is we won't be actually writing our intersection code ourselves, okay? We won't be calculating sphere intersections or quad intersections ourselves. You could actually write your own intersection code following Peter Shirley's book if you want to, but we are actually going to leverage the raycasts or line traces the game engine actually offers us, okay? There are going to be advantages and disadvantages to this, like drop in resolution, and we'll have more finite resolution, like finite points in a mesh, because it's entirely dependent on the mesh rather than calculating with mathematics, right? So keep that in mind. So let's actually define f vector and location, and I'm bringing that up because we are actually calculating the end location. You don't have to do that if you're creating your own sphere intersection code, right? So let's start location this plus ray direction multiplied by, again I'll use an int32 max. Let me make sure I'm recording in my OBS. So yeah, I'm recording. Okay. Let's come back again. So int32 max, and that's pretty much all we need. We can actually go and create our first hit result. We need a hit result for our line traces, right? So hit result, hit result, hit result, and we need f collision query params, and we call this collision params, right? So with that, we can actually start shooting line traces into the scene. So we'll get the world scene or a level pretty much and shoot line trace to it, right? Line trace single by channel and given the necessary parameters actually. So start location, end, or probably not, hit result, start location, end location, and then we need a trace channel, which in our case we're just going to use anything visible, so ECC, visibility, and our collision parameters, right? You actually don't have to use collision parameters here as a separate object. You could use something like ECC collision. I think we have that here. Collision or something similar to that. You could simply use that, but we'll be actually using our object later on when we check for odd or even intersections. So we need to ignore ourselves, right? So this is our first ray into the scene or into the world pretty much. So let's come down here and return a color pretty much, right? So I'm going to actually return f vector of color red. So we clearly see what's going on, right? And out of the base statement, we obviously need another return f vector. I'm going to make this 10, 120, and 235. So it's kind of nice blue color. And let's come up to our render loop and call a pixel color pretty much, right? This is going to be f vector rather than f color. And come back again is equal to ray color. And the depth for now, let's actually just give 1, and the start location is look from, and the ray direction is the ray direction we calculated, or the direction. Okay, I'm not, what's ray direction, right? And pixel color, we can simply come down and say f color color pretty much. Making a lot of typos today, I don't know why. We'll actually call the pixel color x and y. Pixel color dot x, and copy that pretty much along the line. So y and z, right? So now we can just change this to color instead of pixel color. So let's actually debug this. It should work for the most part, and hopefully it works for the most part. So it's compiled, and let's actually see if it works. Okay, so before we do that, we actually need to, let's add a atmosphere. You don't have to do this actually, because again, we're doing a ray tracer. We're controlling every single pixel value inside a ray tracer, but this is just for us, so we have visibility on placing objects in the scene. And we're also height fog, so we can see exactly what's going on. So let's actually put in a sphere, so we have something to intersect. And let's take our camera actor and pilot our camera actor and just position it here and see. Hopefully we don't crash. So yeah, we have our first ray traced image. Now something is odd, obviously. When I move our camera, we have the squished view. Let's actually check why we are getting that squished view. I don't think we are. I think it has to do with something with the viewport width. We cast this, build it again. Hopefully it works now. Yeah, so it works. So make sure you cast the width to the float and divide it by height, and now it works. So wherever camera moves, we have a ray traced image. Now it does feel a little squished, and that's because the viewport is moving. So the viewport moves, the image actually gets squished, right? I have really no solution to that. I haven't thought of it yet. So let's actually change to cinematic viewport. So we'll have a constant aspect ratio, and now it should somewhat work, or not. Okay, we're not, okay, piloting the actor. So let's pilot the actor. So now we have what the camera sees. We are rendering that, right? So there you go. right? So we have our first ray traced ball, but it looks like a sphere, right? So next, let's actually create our first material. And in order to create a material, we need to create a separate class. So let's actually do that. Let me save this quickly and come back to our ray trace CPP. Actually, we don't have to do it in CPP. Let's come back to our Unreal editor, and in our C++ classes, just right click, create a new class, and then another type of actor, and then call it hitable. So hitable is pretty much everything you can hit, right? So if you have a mesh of a ball, we'll actually call the blueprint actor here and then add the mesh to the blueprint actor rather than just dragging a mesh and dropping into the scene. So let's create the class. Sorry guys. So let's wait for the code to compile. And while that's doing that, let's come back to, might be tempted to actually type this. There's actually one tip that I found using Unreal and C++ for a long time. You know, when you create a C++ file, it actually immediately comes in the Visual Studio editor, but don't click it because the Unreal is actually compiling it. It's still compiling it. So if you do something in Visual Studio and before the compilation in Unreal finishes, you'll actually lose the file itself. It won't show up in the editor again. So keep that in mind. So now it's compiled finished, so we can open it up and you can reload all this fine. And come to hitable, and we need to define a couple of things. So let's think about it this way. As I mentioned, the direction of the ray after it hits an object is actually completely dependent on the object itself, though, the material itself. We could actually create a separate material class, but like you might see in Peter Shirley's implementation, but we actually don't have a need to do it because our hitable class is actually the object itself. Because we are doing line tracing, the line tracing actually handles hitting to any mesh at this point, right? We don't have to have a hittable object and let the hittable object have intersection code, right? We don't have to do it. It's pretty simple. So let's, for our case, let's actually come to our hittable hedge and create a private and create a f vector scatter code, right? Now the scatter is going to take in a couple of different values, but for our first implementation of a diffuse material, we're actually going to just take in the ray direction. I don't really think we even need the ray direction. We just need the normal and normal, right? Ray direction and normal, that's fine. And we will create a definition. Bam. Okay. So this is going to be our scattered direction, right? Now a couple of things we have to do is come back to our hittable hedge and define some U property tags or public variables. And let's actually do that. Public, and let's come and type in U property, edit anywhere, and then give it a bool value, and then ask be diffuse. Or just, I don't know, I forgot Boolean conventions for Unreal Engine actually. Is it B is diffuse? It looks kind of odd. So I'm actually going to be diffuse at this point, and by default let's actually turn to true, and we'll have a couple of other properties as well. Be glass and be metal, right? Don't worry about this. We won't be implementing it in this episode, but it's quite scalable, right? So let's actually save that and come back to our scatter function. And in scatter function, we can actually ask if we are diffuse, right? Is B diffuse? And if we are, we need to calculate a ray direction, right? So diffuse materials, or in other words, in layman's term, a rough material, right? So how does rough material actually work? So when the light hits a rough material, it bounces in several different directions, like random directions. That's the point I'm trying to make. Like if this is a, so imagine my hand is a rough surface. It is, okay. So when light hits it, there's no definite path it will take. It could take, literally, it could go there, there, it could go up, it could go there, there. So that's what we're modeling here. Take, when it hits a point, take the random direction to that point, right? Or random vector from that point, essentially. So again, if light hits something, it has to reflect, refract, or let it pass through. So transparency, right? So diffuse is pretty much the easiest to model because we are just taking a random point above the hit point and just saying hit point minus that random point is the new direction and shoot that ray in that direction. So we'll get a diffuse shader. I'll try to put up some images on the screen of what I'm talking about, but I think when we're coding it's going to be a little more clear. So B diffuse is actually, how are we going to deal with this? Let's think about this. Ray tracer. So I'm actually going to hide all these functions. So this is the only thing we're going to focus on right now. We'll actually call hitable object. So the get actor. So let's actually try to do that. So a actor, right? Actor, hit actor. I'm trying to think of a way to do this neatly. Hit result, get actor, right? So we need to cast this actor into our hitable object. So hitable object, we need to actually include this. So let's come up to a ray tracer h, and ray tracer generated include hitable h, right? So that should be more than enough. Hitable, or a hitable, right? So okay, obviously pointer, and we're actually going to cast it to a hitable. Get actor a hitable. So the actor itself will be a hitable object. So as I mentioned, we'll take the hitable object as a blueprint and then add a mesh to it, and then we'll convert the actor into a hitable object. So that's what we're doing here. We're casting it to a hitable type, which the object is. So if this is not a hitable type, you'll get an error, right? So once we did that, we'll actually come and say, so now we can actually access the function. So if I come down and say scatter, we actually do not have scatter, okay? Hitable scatter, private, okay. I think this is the problem. Actually put it at public, and now we should be able to save that quickly, and scatter should be a function. Yeah, so we have scatter. So scatter takes in a ray direction and a vector 3 normal, right? A vector normal. So this is how we're going to do it. The thing is going to return a ray direction. So we'll actually call the line trace again, so the ray color again. So actually call this here, and we'll need to pass in the start location and the end location, right? So start location is actually going to be pretty simple. It's going to be hit result dot impact point, or hit result Okay, hit result dot impact point. It's supposed to be, why is it not working? Ray color. Okay, we need the depth. Obviously, we need the depth. -1, and we'll call that hit result dot impact point, and the ray direction will actually calculate f vector scatter direction, and we'll just keep this there, and we can scatter direction, right? So now we have it's fine, let's just do that. We have a proper thing going on. So scatter is impact point. So let's actually define a couple of variables to not make this cleaner. So I'm going to define a location called hit location, and then get the impact point of that, and f vector hit normal. Yeah, I think hit normal is fine, and get the hit result dot normal. So that's what we're going to do. We're going to actually give the hit location here, hit location, and our scatter direction. It's fine, right? So let's come here, and we have, what do we have? Ray direction. So the ray direction is the incoming ray, so that's fine. And the hit normal. So hit normal. So that's our first step. So our code here is done, but we need to come back to our hitable object and define a bead diffuse. So let's actually get into it. I think in order to do that, let's actually define a separate class. So I'm going to name this actor again, ray utilities, right? So this is actually going to contain all those math functions, if you will. Create class. So once you have that, we just reload it all again in ray utilities, and let's come into our ray utilities edge, and then come down to public, and then let's actually define a couple of functions. I'm actually going to create a different public, again, just to keep the code base cohesive, right? Let's actually think about this. So we need a random vector, as I mentioned, to get the scatter direction for a diffuse material, actually. So first we need to define a double and random double in range. We'll give it a double min and a double max. So public, okay, let's actually not do this. Let's actually define them in the header file, or the CVP file, actually. So random double, we have that. Let's actually come down and say random float random float is equal to fmat rand range min and max. Am I missing something? Why is it? Okay, obviously min max, and then double random double is equal to static cast it into double, and then we'll just random float, pretty much, right? And then we'll return the random double, right? So we have a random double function, pretty much gets a random value between I said range, and we need to define one more function here. That will be f vector vector get random unit vector. So random unit. Or maybe I'm just going to name it here. I'm going to say get random double in integer, or maybe not. It's too long. So get random unit vector. It's actually not going to do anything. So let's, I mean, the parameters actually not. It's actually going to do something, but define it here and then come to our random unit vector, and we're actually going to define while true auto p is equal to I don't know, wait, are we defining our vectors this way? So it's going to be get random double in integer, so random double in range, and -1 and 1, and then just copy this up, and we should have if p dot squared length less than 1, return p. I think I'm missing something here. Not really. Squared. No, it's not. Okay. I don't know if it's working or not. Actually gonna put an f vector here. Vector is equal to f vector double range, and I'm gonna say squared length is a function call less than 1, return p, and return p dot get safe normal actually. Okay, so this is actually going to be a random unit vector, and hopefully it works. Hopefully we don't have any logical errors, because that's going to be a big problem. So yeah, we have an error. So why is this not working? This guy is supposed to be matching this guy. Okay, the while loop, we don't have a closed bracket for a while loop, so I think that should be free syntax. Okay, so now we're working. So let's come back to our hitable list. Hopefully it works. All we need to do is we need to return a direction. So that's what the scatter function is doing. So normal plus random unit vector. So we need to actually add it here. So let's come back to edge, hashtag include ray utilities dot ray utilities dot edge, right? So come back to this guy, random unit vector So just give me a second, guys. I'm actually confused. So the hitable object, so the random unit vector, so the ray utility scatter function actually in the hitable object. Okay, so we can't. Okay, so we actually need to create an object of the type hitable or ray utility. So I think that's the problem here. So let's come to begin play, or rather come here, the hitable object in public. I'm actually going to test this out. Actually, I'm just going to put it here. I'm going to say ray utilities, ray utils and come back to here, and then in the begin play I'm actually going to say ray utils is equal to create object. So give me 1 second, guys. Let me figure this out. So yeah, the problem here is new object, not create object. Silly error actually. So let's come down to our diffuse again, and now we can actually call ray utils, and we can actually call the random unit vector. So that pretty much should be it. Random unit vector direction, and if it is not diffuse, we'll just return ray direction, I think. Let's not do anything complicated here. So let's try to compile all this. Hopefully we don't have any errors. I think we have some error because it's taking a lot of time. So okay, so we don't have actual errors here. So let's try to work this out in the ray utility. So ray tracer or CPP. We have, I don't really want to see the initialize function anymore. Shadows color is defined in location, get, and the sky color. So the ray color here, I'm actually going to type in 0.5 times, so the amount of absorption. So the 0.5 is how much from the previous recursion we are absorbing the color, right? If it is 1, we're actually going to see the same color throughout the entire viewport. If you're putting like some value like 0.5, now slowly we actually decrease the value, so we can have some cool shading going on. We could actually replace this with our own color, which we'll do later. We could have a public statement to choose colors and then multiply that color here. So let's actually check. Let's come back to our demo class, I mean Unreal Engine, and come to our blueprints and create a new hitable object. So hitable here, and create it, and we're going to name it as hitable, and we're going to call this ball. Okay, so when you open it up, go to your blueprint editor and add a sphere mesh and drag it onto the default scene root, right? And then another thing you want to do is go to the hitable self and make sure you have ticked diffuse on. So I forgot, I actually ticked everything on. So let's come back to our project here and go to a hitable class again, hitable edge, and then convert everything to false pretty much. And compile this again. Hopefully don't have any errors. Okay, yeah. So we have 2D here, and yeah, now we should have just that. Compile and save the blueprint and delete the ball mesh if you haven't already dragged that, and put the hittable object there. And let's, fingers crossed, we don't have any crashes because I haven't really make sure we're piloting the camera actor. And oh yeah, we need to actually set the ray depth. So come to a ray trace manager, and we don't have a ray depth. So thank God I actually caught on. I'm actually going to close this. It's my previous project I'm using for references here. So yeah, let's come back to our ray tracer. And I completely forgot this because when we're doing the initial call in the render call and the render function, we're not rake color, so 1 is going to be the max depth. So we actually don't need that. We'll actually call a max depth value, and then come to our ray tracer. In our public statement, we'll actually define a U property of a max depth value. So max depth is going to be type integer, and it's actually going to take in a value of, by default, let's actually put 10. One thing you might notice is as you move on exponentially, not exponentially, the higher the values you go, the lower the difference you get. So 1 to 10 obviously has a big difference, but 10 to 20, not that much of a difference, and 20 to 100, again, the difference is reduced. So I think we call it exponentially. I have no idea. Inversely, I don't know. I don't know math. So let's actually build this. So we have an int of max depth 10. So what that means is we'll have 10 bounces pretty much, right? Light bounces. Think of it that way. Don't think of it as depth. It's just how many times your light bounces before it reaches a shadow base statement. So let's come back, and we have 10, 20 and all that. Let's try to run this, and we have something. So let's come closer. So yeah, we do have something going on in the screen. I think I might have forgot to do something here. Let's come back to our ray tracer, CPP. Let's actually put this on the first and the hitable second, and the rate is class last. We don't need the demo class anymore. Let's come back to CPP. I think we need to add a alpha value to the start location. I'm not really sure, so let's come back, and start location is equal to start location plus, let's say, 0.001 multiplied by ray direction. So we're just adding a small offset to the start location, and we have something going on. I have no idea what's going on, but we do have something going on. So let's actually add a different hitable blueprint here. So hitable object, and then we'll call this hitable plane, right? And then come to our plane, add a plane, put a default root, and scale this up to be fairly big, so 50, and compile and save. And this is actually going to be diffuse as well. So let's close this up. Everything should work as it should. 0, 0, and 0, and 0, 0, and 0. So let's come up. So there you have it. So let's try rendering this. So yeah, we are seeing something. We are seeing shadows and a little bit of light as well, but it's not extraordinary to look at. So yeah, so that's our first ray traced diffuse shader. I think we are, so I think the samples is a problem here. We don't have a sample yet because we need to actually do anti-aliasing for that, anti-aliasing for that. But let's try to increase our sample count, or the render a max depth pretty much. So let's put 20, and let's put 500 for the resolution, and let's see if anything changes. So yeah, we have much more a realistic render here. So one thing we can do is come back to ray trace and actually decrease the amount or increase the amount of light that actually absorbed or gets absorbed. And another thing we can do is actually put everything as 255, the background color I mean, right? Let's come back up. So yeah, we have something going on, but it's not great. That's all I can say. We have, let's actually increase it to 1000. So yeah, that's much more realistic, so to speak. Or maybe we are not normalizing the direction. So in the scatter function, let's actually ray direction is equal to ray direction dot get safe normal. This might actually be the problem. So let's come back and hit play. Yeah, so now we have a kind of realistic, it's not realistic, but we're getting there slowly. And this is a start. So we have our first ray traced sphere. So I did some debugging off camera and I actually didn't find any errors. The only problem here is we don't have anti-aliasing, and because of that we need to up the resolution to a significant amount before we have a good amount of color values. If you get what I mean, we get good samples of color values. So as you can see here, this kind of looks somewhat okay because I increased the resolution of the ray tracing to 4000. So the width itself is 4000. So that's why we have this nice diffuse shader looking thing, material looking thing. And if you look closely, we also have these lines going in the sphere. As I mentioned, if you're using line traces or ray casts, there's actually advantages to that and also disadvantages to that. Advantage is that you could use any mesh, really. You could make a mesh in Blender and throw it inside Unreal Engine and click render and it would render a ray trace image. It's simple, right? But the downside is that it actually shows the poly count actually. So we have the default sphere in Unreal Engine, which is significantly low poly. So we can actually see the polygons as those lines. So these lines you're seeing here is actually the edges of the sphere. So in the next episode, we'll actually implement a anti-aliasing, which will probably solve most of the issues here. So when we zoom in, we actually have jagged lines and all these shadows are splotched. But when we do implement anti-aliasing, we'll have some sort of control to the sample count we can introduce per pixel and the amount of rays we can shoot through per pixel, right? So with that said, we have our first ray traced material and our first ray traced image. Yeah, so with that said, I will see you guys in the next episode. Thanks for watching. Also, I forgot to mention, I have a Patreon. So if you guys want to support my work, you can also get access to my project files and source codes. And I'm also thinking about introducing more content there, like PDFs and sort of things like that. So if you guys want to support my work and my channel, you guys can do so in my Patreon. So finally, with that said, I will see you guys in the next episode. Bye bye.